In this video, we're going to start looking at what we call periodic trends. These are trends in the properties of atoms that vary across the periodic table, and trends that we can see as we go from left to right across the table and from top to bottom down the table. And so the first thing we're going to look at are the sizes of atoms and ions. We're going to look at a few other properties of atoms over the rest of Chapter 7, which will conclude our discussion about what's happening with electrons in atoms and ions. So first we're going to talk about what do we mean by a size. So this figure from your textbooks explains it quite well. Different elements participate in different sorts of bonding, right? So we have a covalent bond, or like a molecular system like Cl2 here, or we have a metallic system like sodium here, where there's a bunch of sodium metal atoms right next to each other, or we have ionic bonding like sodium chloride. In all cases, what we're considering is how far, what's the distance between two atoms, and what we consider their size is what we're going to look at here is what we call the radius here. So the atomic radius is how far apart these are from each other. And so for different types of elements, we're looking at different sorts of ways we measure this, but the overall idea is basically just, again, this is all thinking about probabilities, but there is some size to the atom, and we're looking at, if two atoms come next to each other in some sort of bonding, what's the radius of sort of the sphere that they make when they're next to each other. And so that's what we're looking at, is this what we call the atomic radius. Now the scale of this, as the units are indicating here, these atoms are roughly on the size of picometers, so they're really small. And so something like chlorine, for example, has 99 picometer radius, sodium has 186. So let's look at some data. So I'm going to scroll down here. This is, again, from your textbook, but this is data that's been measured for different atoms. And we're skipping over the D block elements just to make this trend a little bit more clear. So you may notice there's a break here. Let me draw in red on this. There's a break here between, we have the S block here, and we have the P block here. We're mostly going to focus on these. But as we go from top to bottom down the periodic table, there's a pretty clear trend in atomic size, as if we look at a particular column here. So let's look at, say, column 14 here. Carbon has an atomic radius of about 77 picometers, and as we go down, that keeps getting bigger and bigger as we go until we get down to lead, which has the largest value. And that trend holds pretty well, with some exceptions. There's something weird going on with aluminum here. But for the most part, this trend holds. The atoms get bigger as you go down the periodic table. And the reason for this is pretty straightforward. We are filling, as we go down the periodic table, we are filling orbitals with higher n values. And as we learned, n tells us about the size of the orbital, or the average distance of the electron from the nucleus. And so as we're putting electrons into these higher n value orbitals, they are on average farther away from the nucleus. What that translates to in terms of the size of the atom is just that the atom gets bigger. So that trend's pretty clear to see and pretty simple to explain. A electron in a 2s orbital in lithium is a lot further from the nucleus than an electron in a 1s orbital, like hydrogen. So we can see that trend as we go down the periodic table. We're filling orbitals with higher values of n. What about going left to right across the periodic table? Well, you might expect we're putting more electrons into the orbitals. Maybe they get bigger, but we see in fact the opposite trend. As we go left to right, say looking at the n equals 2 here, from lithium we start at 152 picometers, but by the time we get to neon, we're down to 69. So it's gone about half the size. So there's a pretty clear trend that atoms get smaller as we go left to right across the periodic table, right? So as we go down the periodic table, they get bigger, but as we go left to right, atoms get smaller. Okay, so let's explain what's going on here. So the main thing that, I'm going to swipe to the side over here to give myself some space to write. The main thing that's going on here is what we call the effective nuclear charge. And what's changing as we go left to right across the periodic table, we're adding electrons, which you would think would cause the electrons are going to push on each other. Because they're negative, they have a repulsion. So as we add more electrons into the atom, they should push on each other and push each other apart more. But the other thing we're also changing is the nucleus, the number of protons in the nucleus. And we're adding more protons and more positive charge in that nucleus. So as we go from left to right across the periodic table, we get additional charges in more protons, a higher charge on the nucleus. That higher charge for the electrons is going to pull on the electrons more. So here it's an attraction. So these are competing effects, right? The electrons are pushing on each other. They have this repulsion. But the nucleus and the electrons have this attraction, and they're pulling on each other. So if the electron-electron repulsion matters more, you expect to have bigger atoms. But if the nucleus pulls on the electrons more, then you expect the atoms to get smaller because the electrons will be, on average, closer to the nucleus because they're getting pulled on by the protons. And so as we go from left to right across the periodic table, what's happening is that this charge is increasing, but we also have some electrons sort of close by the nucleus that are only partially shielding that positive charge. So you might have, say, 1s electrons that are close to the nucleus, and this positive charge keeps getting bigger, but you don't have any more core electrons. The core electrons stay the same as you add valence electrons. And so these valence electrons experience a higher effective nuclear charge, what we call Z effective. Z, again, being the number of protons, but the effective nuclear charge increases as we go left to right across the periodic table. And this effect matters more, right, than the electron-electron repulsion. So this trend that they get smaller is due to this higher effective nuclear charge, that these valence electrons are pulled on more by the more positive nucleus. And the other electrons in the atom are not able to do any additional shielding because we haven't added any more core electrons, just valence electrons, and they don't shield each other from the nucleus. So that's the explanation for why, as we go left to right across the periodic table, we see this trend that atoms get smaller. One final note is, I also mentioned at the beginning that we'd talk about ions as well. This one's pretty straightforward. As we look at positive ions and negative ions, there's a pretty clear trend in what happens to the ions. So with positive ions, we're losing electrons from their valence shells. And so if we think about lithium, we have an electron in a 2s shell, and that leaves when we go to lithium plus. And so we're left with only 1s electrons in this case. And so that lithium ion becomes much smaller. Those two of us, right? We've lost all the electrons that have the higher n values that are bigger orbitals, and so we're left behind with only the small core orbitals. So positive ions will always be smaller than the atoms that they start from. And that effect becomes more pronounced the higher the charge is. So when you lose more electrons, the nucleus is able to pull on those electrons even tighter. And so see beryllium 2 plus is an incredibly small, has an incredibly small ionic radius. Same thing with aluminum 3 plus, where we've lost 3 electrons. It becomes a very small one. Anions, on the other hand, our negative ions, have the opposite effect. Because we're adding electrons in but not changing the nuclear charge at all, here the electron repulsion matters. And so we see an increase as we go from the neutral atom to the ion for anions. These are always bigger, right? Anions get bigger, whereas cations always get smaller. And similar to how a higher charge leads to a more pronounced effect for aluminum 3 plus, we see the same thing. There's more of a change when we go from oxygen to oxide to the O2 minus ion, because we have added now 2 extra electrons instead of just 1. So that leads to additional electron-electron repulsion. And so that concludes this section on our first periodic trend we're looking at, which is atomic size and ionic size.